Hello and welcome to this video tutorial. Today we're going to look at Skills Practice 8.3, Universal Gravitation. Newton's law of universal gravitation states that every mass in the universe, every object in the universe, attracts every other object in the universe. And so to calculate the universal gravitation, meaning the gravity of something, the gravitational attraction of something, let's say off the surface of a planet, just anywhere between any two distances, all you need are those two masses and the distance that separates them. Let's take a look at the variables involved. If we look at the picture here, we can see a picture of the Earth and a satellite, which we can assume to be the moon. F is the force, more importantly, the gravitational force. Now you can see from the arrow that we have a little bit of Newton's third law applying here too. While the Earth is pulling the moon towards it, the moon is pulling the Earth towards it with the exact same amount of force, okay? So whatever force we find is the same for both parties, okay? But F stands for gravitational force of attraction between two masses. Big G is referred to as the gravitational constant, and the number we're going to substitute for it is right here. 6.67 times 10 to the negative 11. Don't worry so much about the units. You can't put those in a calculator at the moment anyway. The two masses, of course, would be mass 1 and mass 2, noted as m1 times m2. And finally, r. R is not the radius. R is the distance between the masses. More specifically, the distance between the center of the masses. Not the surface-to-surface distance, but the center-to-center distance. If you had two spheres that were touching, R would not be this distance here. R would not be 0 since the two surfaces are touching. In fact, if two surfaces are touching each other, R would be the distance between the two centers. In this case, R would be 0.6 when you add those two together. Let's take a look at the variables one more time. Jot this down if you need to. If you see newtons in a problem, that is the gravitational force, F. If you see kilograms, that is going to be mass 1 and mass 2. If you see meters, that's going to be some sort of distance. Now, in order for it to be R, it has to be the distance between the center of masses. And then finally, if we're always given G, and we're always going to be putting in this number, 6.67 times 10 to the negative 11. Let's begin. Number 1. Calculate the force between two objects that have masses 70 kilograms and 2,000 kilograms. So we can call this mass 1 and mass 2, separated by a distance of 1 meter. That would be R. So we're looking for force. We have 70 kilograms, 2,000 kilograms, and 1 meter. So that's mass 1, that's mass 2, and that's R. The equation we're going to be using is our universal gravitation equation of F equals big G, the gravity constant, times m1 times m2 divided by r squared. Now, we're going to plug into that just like this. Let's zoom in so we can see it better. And this is exactly how we'll put it in our calculator. In our calculator, we'll put open parentheses, our value for G, which is 6.67 times 10 to the negative 11, times the first mass, which in this case is 70, times the second mass, which in this case is 2,000, close parentheses. So we're going to group those three terms being multiplied times each other with two parentheses on the outside. Then we're going to hit divide in our calculator. Then we're going to open parentheses again, put our distance, in this case 1 meter, and then we have to hit close parentheses and square. Let's take a look at how this can be entered in our calculator. open parentheses, 6.67 E negative 11 times our second mass, 70, times our second mass, 2,000. Once we do that, close parentheses. Okay, now we're going to hit divide, open parentheses again. We're going to put R. Our value for R in this problem is just 1. Close parentheses, hit our squared. Final step, hit equals, and we'll go ahead and be able to divide the top by the bottom. And we get 9.3. Now, if you have to move the decimal 1, 2, 3, 4, 5, 6 places to the right, it's 9.3 times 10 to the negative 6 newtons. Please make sure you practice putting this in your own calculator, as your calculator might be slightly different operations than mine. Number 2, calculate the force, we're looking for F, between two grapefruits touching each other, each with a radius of 0.08 meters and each with a mass of 0.55 kilograms. All right, so here's what's going on. This is going to be mass 1 and mass 2. It's going to be both. So mass 1 equals mass 2 equals 0.45 kilograms. But R is not 0.08. Like, draw a picture and you'll see it more clearly. We talked about this earlier. When we have two objects that are touching, right, the R would be the distance from center to center. So if one grapefruit has a radius of 0.08 meters and the other has a radius of 0.08 meters, that means R is 0.08 plus 0.08. R is 0.16, right? Or the sum of those two radii. Okay, you're always given G. Okay, so F equals big G times M1 times M2 divided by R squared. So F equals, we're going to go 6.67 times 10 to the negative 11 times 0.45 times 0.45, close parentheses. Then we're going to hit divide, open parentheses, 0.16, close parentheses, squared. Let's try and get this entered in our calculator. Open parentheses, 6.67 E negative 11 times 0.45 times 0.45, close parentheses. Divide, open parentheses, 0.16, close parentheses, squared. Okay, we have a really small number there. And to get this in proper scientific notation, you're going to have to move that decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times to the right to get 5.3 times 10 to the negative 10 newtons. Again, please remember to pause the video to perform these calculations yourself. Number 3, calculate the force between one grapefruit, so that would have a mass of 0.45 kilograms, we'll call that mass 1, and the Earth. Earth has a mass of 5.9742 times 10 to the 24 kilograms. That would be mass 2. And a radius of 6.3710 times 10 to the 6. Assume the grapefruit is resting on Earth's surface. Well, again, if we draw a picture, here's the Earth. There's the little grapefruit. you can see the distance from the center of the grapefruit to the center of the Earth is, for all intents and purposes, the radius of the Earth, because that little grapefruit has 8 centimeters right above the center of the Earth. That's not a whole lot. So what we'll do is we'll consider the radius of the Earth this time, the distance between the two masses, r. So mass 1, 0.45 kilograms. Mass 2 is 5.9742 times 10 to the 24 kilograms. And r is 6.3710 times 10 to the 6 meters. The equation we're using, again, is F equals big G times M1 times M2 divided by R squared. So we're going to go big G, 6.67 times 10 to the negative 11 times first mass, 0.45 times second mass, 5.9742 times 10 to the 24th power. Divide that by the distance, 6.3710 times 10 to the 6, square that. Opening parentheses, 6.67 e negative 11 times 0.45 times 5.9742 times 10 to the 24th power, close parentheses. Now we're going to hit divide, open parentheses, 6.3710 times 10 to the 6, close parentheses, squared. And we get 4.4 newtons. Number 4, a man on the moon with a mass of 90 kilograms, we'll call that mass 1, weighs 146 newtons. Well, newtons is your force, your gravitational force. If the radius of the moon is 1.74 times 10 to the 6 meters, find the mass of the moon. We're looking for M2. But again, the radius of the moon, a man standing on the radius of the moon, the distance between the center of the man and the center of the moon would essentially be the radius of the moon. So we will call this R. So mass 1 is 90 kilograms. Force F is 146 newtons, and R is 1.74 times 10 to the 6 meters. Again, we're using the same equation, F equals big G, M1, M2 divided by R squared. Now here's the difference. You're solving for M2. Well, in order to do that, you have to get rid of this fraction, G M1 over R squared. So let's see how we do that. First, let's go ahead and write the equation. Leave some space. Then it's G times M1 times M2 divided by R squared. And what we're going to do is we're going to multiply both sides by the reciprocal of this fraction right here, which would be R squared divided by G M1. Notice R squared cancels, G cancels, M1 cancels, M2 is all by itself. Do this to both sides. And M2 would equal F times R squared divided by G times M1. And that's what we're plugging into right now. So F, well, actually I can just plug it in up here. F would be 146 times R squared, 1.74 times 10 to the 6 squared over G, 6.67 times 10 to the negative 11 times M1, which was 90. Now here's how we're going to put this in our calculator. We're going to go 1.74 times 10 to the 6th power in parentheses, square that. Then we'll go ahead and multiply by 146, We'll hit equals on that. Then we'll divide, open parentheses, 6.67 times 10 to the negative 11 times 90, close parentheses. Let's give this a try. Okay, open parentheses, 1.74 times 10 to the 6th power, close parentheses squared, times 146 equals. Now we're going to divide, open parentheses, 6.67 e negative 11 times 90. Again, close parentheses. Now we're going to hit equals to divide the top by the bottom. And we get 7.36 times 10 to the 22nd power. Number 5. For m equals 5.9742 times 10 to the 24 kilograms, and r equals 6.378 times 10 to the 6 meters, what is the value given by this equation? Well, here's the equation we're going to work with. G equals big G m over r squared. Okay, write down your answer and simplify your units. Okay, well, here's how the units would simplify. Okay, and I'm going to do this over to the side. Now, G has a really strange set of units. Okay, so I'm going to write the equation is this. Big G m over r squared. So for big G, the units for big G are actually newtons times meters squared per kilogram squared. Okay, that's it. Okay, then meters, you have meters right here. Mass, which would be kilograms. Okay, then over here you have R, which is meters squared. Okay, so now let's kind of clean this up a little bit. Well, a newton itself, 1 newton is a kilogram times a meter per second squared. So I'm going to substitute for that. We're going to go kilogram meter per second squared times the meter squared here divided by the kilogram squared there times the kilogram over here divided by meters squared. Okay, look at what's left. Cancels, 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 cancels. What are we left with? Meters per second squared. So meters per second squared is the unit for acceleration. And so what we're basically getting is the acceleration due to gravity. Okay, let's go ahead and evaluate this. Okay, we're looking for little g. Okay, we're given a mass of 5.9742 times 10 to the 24 kilograms, and we're given an R of 6.378 times 10 to the 6 meters. The equation we're using is big G, m, which is the mass of the Earth, divided by the radius of the Earth squared. So 6.67 times 10 to the negative 11 times Earth's mass, 5.9742 times 10 to the 24th kilograms. We're going to divide that by the radius of the Earth, 6.378 times 10 to the 6 squared. Clear? Open parentheses, 6.67 times 10 to the negative 11 times 5.9742 times 10 to the 24th power. Close parentheses. Divide, open parentheses, (6.378) times 10 to the 6, close parenthesis, squared. And we get 9.795. What is that? That's 9.8 meters per second squared, otherwise known as the acceleration due to gravity on the surface of the Earth. Okay, so we find the acceleration due to gravity on any planet by simply knowing the planet's mass and its radial distance. Number 6. The distance between the Earth and its moon is 3.84 times 10 to the 8 meters. There's R. If the Earth's mass is 5.9742 times 10 to the 24, mass 1, and the mass of the moon is 7.36 times 10 to the 22, well, there's mass 2, what's the force? Okay, so let's see what we're given here. Mass 1, 5.9742 times 10 to the 24th power. Mass 2, 7.36 times 10 to the 22nd power. And R, 3.84 times 10 to the 8th power. You're again using the equation F equals big G times M1 times M2 over R squared. So let's go 6.67 times 10 to the negative 11 times 9742 times 10 to the 24th times 7.36 times 10 to the 22nd power. All of that is over 3.84 times 10 to the 8th power squared. Let's go ahead and try and put that in our calculator. Okay, open parentheses. 6.67 times 10 to the negative 11 times, well, Earth's mass, 5.9742 times 10 to the 24th power, times moon's mass. That would be 7.36 times 10 to the 22nd power, close parentheses. Divide, open parentheses, the distance between the center of the Earth and the moon is 3.84 times 10 to the 8th, close parentheses, squared. And we get about 1.99. If you want to round that up to 2, that's fine, 2.0. 1.99 times 10 to the 22nd power. To the 20th power, excuse me. 1.99 times 10 to the 20th newtons. That answer should make sense to you. Earth and moon are two pretty big masses. It should make sense that there's a lot of force attracting the two of those objects. Question 7. A satellite is orbiting the Earth at a distance of 35,000 meters. If a satellite has a mass of 500 kilograms, what is the force between the planet and the satellite? Well, you've got Earth's mass. Okay, we're looking for force. Earth's mass, we can call that mass 1, I guess. That would be 5.9742 times 10 to the 24th kilograms. Now, I'm getting that from previous problems. Obviously, it wasn't given in this problem, but I'm given it in other problems. Mass 2 is the mass of the satellite, 500 kilograms. And R is not 35,000. Let's see a picture. Here's Earth. Here's satellite. Now, the distance between the center of the satellite and the surface of the Earth is 35,000. But R goes to the center of the Earth. So you need the radius of the Earth, which was 6.378 times 10 to the 6th power. Okay, so we need to add those. 6.378 times 10 to the 6th power plus 35,000 is 6.413, or 6,413,000 meters. Okay, plugging in for force. 6.67 times 10 to the negative 11 times 5.9742 times 10 to the 24th power times 500. Close parentheses, divided by 6.413 times 10 to the 6th power squared. Okay, let's put this in our calculator. Open parentheses, 6.67 times 10 to the negative 11 times Earth's mass, 5.9742 times 10 to the 24th power, times the satellite's mass, 500. Close parentheses. Divide, open parentheses, 6.413 times 10 to the 6th power, close parentheses, squared. And we get about 4,844.5, or we could round that up to 4845. Now, something to consider about this answer. On the surface of the Earth, the satellite would weigh 500 times 9.8, or 4,900 newtons. Going 35,000 meters in the sky, the gravity should be less. So that answer should make sense. Okay, now in our final question, we have the mass, this is question 8, the mass of the sun is 1.99 times 10 to the 30. We'll call that M1. And Earth, we're given Earth here, so you're going to have to use Earth's mass again. We already know what that is. And the average distance between them is 150 times 10 to the 9 meters. We're looking for force. So M1, sun's mass. M2, Earth's mass. R, 150 times 10 to the 9 meters. Using the same universal gravitation equation. Okay, plugging into it, F would equal 6.67 times 10 to the negative 11 times 1.99 times 10 to the 30 times 5.9742 times 10 to the 24th power. All of that divided by 150 times 10 to the 9 quantity squared. Let's see what we get. Open parentheses, 6.67 times 10 to the negative 11 times 1.99 times 10 to the 30 times 5.9742 times 10 to the 24th power, close parentheses. Divide, open parentheses, 150 times 10 to the 9, close parentheses, squared. And we get about 3.5 times 10 to the 22nd power. Again, that answer should make sense, as the Earth and the Sun are two very large masses, so it should be a very large amount of gravitational force attracting them. I hope you found this tutorial to be helpful. Again, I can't emphasize enough, please pause or rewind the video to various examples and attempt these independently.